we're going to do a quick math review. Woo! Okay, so get rid of that. What I want to do is just run through everything that we've been doing in terms of math through this entire module. And we're just going to go back through it. So you'll have one video that you can go back to find everything, so you don't have to go back through all of them. Okay, so first, we want to find frequency. In a simple tone. I'm going to put our formula down here. F equals 1 over T. That's our formula for finding frequency. So in a simple tone, we're going to have a wave like that. And this period here is going to be 0.02 seconds. So if we put it into our formula, we've got frequency equals 1 over 0.02. And that means that frequency equals 50. 50 what though? What's the units here? It's hertz. So frequency equals 50 hertz. Okay. So get rid of the rest of this. Oh, I should have left the formula. Oh well. We can just put it back in. So now it's not frequency in a simple tone, it is frequency in a complex tone. And that means, what does that mean? That the formula for frequency is exactly the same. 1 over T. It just means that it's a little bit more difficult to find the actual T. So okay, it's not a good drawing, but it'll do. It's like a bunch of 10-gallon hats or something. So we're going to go from, let's change this color. So we're going to go from here to here, because that's about where that wave starts again. In this case, if you were going to go from peak to peak, like we talked about earlier, a different way of measuring the wave, you need to be really careful to go from the right peak to the right peak. So you wouldn't go from peak to peak like that. That's definitely not enough. You'd go from peak to peak like that. So you have to go from identical peak to identical peak. Obviously here, trough to trough is just fine, because there's only one trough. So you go from identical peak to identical peak, or where this wave begins to where this wave begins again, where it replicates itself. And what you end up with is, let's say that the time is 0.08. Let's say 008. So it's 0.008 seconds to replicate this wave. So one cycle time is 0.008. Frequency equals 1 over 0.008. And I have a calculator here because I can't do that in my head. It is 125 hertz. Okay. So let's move on to adding two waves together. All right. So let's say you have a wave. Here's one wave. Here's a second wave. And we're going to change the color of these. So the first wave is going to be kind of a little guy. Not a lot of amplitude here. The second wave is going to have more amplitude, but not, a ton. Not max amplitude. And I'm trying to keep them in phase, but that is not, I'm failing. There we go. Okay. So the amplitude, we can use a different color for this. So amplitude here is going to be 0.3. And amplitude here is going to be 0.5, the max amplitude, or min. And so literally what you do is when you add waves, you just add the amplitude. So if this is going all the way to 5 and this is going all the way to 3, we're going to have a new wave that goes all the way to 8. They're in phase. So, uh-oh, sometimes that happens with my touchscreen. And it's happening again. There we go. All right, so that was crazy. So these are in phase, which means that they're lined up with each other. And that makes it really easy to add waves. That means that the max amplitude here is 0.8. One of the reasons why, let me erase all this again. If you remember from the lecture before, if you have two waves that are opposite, they'll cancel each other out. That's because they almost literally, they just cancel each other out. So you have a wave here, amplitude 0.5. And you have this wave here, also amplitude 0.5, but it's out of phase. It's 180 degrees out of phase. So, again, I want to try to match them, but I'm not good at that. Down, up, okay. Not the best, but it's it'll work. Okay, so this is 0.5. This is 0.5 to the top of that. But they're out of phase. So when you add this negative 0.5 down here to this positive 0.5, negative 0.5 plus positive 0.5 is 0. So this wave comes out to be, when you add it together, a flat line because everything cancels out. It's completely out of phase. So everything cancels each other out. Okay, we can do this again. I mean, you probably have the concept by now, which is great. If you have a wave this is 0.6, and then you have this other wave that's 180 degrees out of phase. But it goes to negative 0.5. So it's the same wavelength, the same frequency. It's 180 degrees out of phase, but they don't have the same amplitude. This wave has more amplitude. It's a little bit louder of a signal. So then what's going to happen? Well, 0.6 plus negative 0.5 equals 0.1. So what you have is a signal that's just dampened. You're going to still end up with a sine wave. I was going to say sinusoid, but same thing. You're still going to end up with a sine wave, and it's still going to be the same frequency, but it's going to be really ultra quiet. Like that. Okay, so that's adding waves. What do I want to move to next? Oh, how we can figure out the frequency when we're not right on the mark. All right. It just adds one more step. Okay, so frequency when we're off the mark, pretty easy. So we've got wave, and then we're going to have these little tally marks, but they're going to be in funky places. So we're going to have our first one here, and then should have another one there, but we don't because we have one there. And so those are going to say like 0.001 and 0.002. So the resolution here is in, this scale. Again. Okay, there we go. So the resolution here is in the scale of 0.001, 0.002. They're not giving us anything less than that. You could infer that your wave is starting over at 0.0005, but we don't know that for 100% sure. So what you want to do is you want to count up the number of cycles that are in the mark that you see. So we've got 2 cycles. Oh, it's happening again. There we go. So we've got I'm just going to have to erase this because I can't write over that. Okay. 2 cycles in 0.001 seconds. So what do? Well, we take 001 and we divide it by 2, and that does in fact give us 0.0005. And now we do our usual formula. What's the formula? Frequency equals 1 over t. This is t. I've run out of room to write, so frequency equals 1 over 0.0005. 1 over 0.0005 is 2,000 hertz. 2,000 hertz is your answer. Great. Now you get to watch me erase again. I mean, at least I'm not like having to erase, in typical fashion, like just erase a bunch of different pieces of paper. Okay, there we go. Now, what did I have on here that I wanted to look at next? Finding FO in frequency domain. Well, that's super easy. I'm not even totally sure why I wrote that down, but let's take a look at it. All right, so here we're in the frequency domain. So we've got a graph that's going to go by frequency and amplitude, and it's very easy to figure out what the frequency is because you're going to have these bars. And they'll say underneath things like 100 hertz, 200 hertz. And so then you just say, well, this frequency is 100 hertz. That would be the fundamental frequency, right? Because it's the lowest frequency, it's the carrier frequency, if you were to think about it that way. So if we drew this out, the frequency might look like, or sorry, the wave might look like that. You can see in there that you've got what's called a carrier frequency, right? It's this one. You can kind of draw a dotted line right here. And if you drew a dotted line over this the shape of this wave, you end up with this 100 hertz tone. That's what I've got in the blue little dotted lines. That's called the carrier frequency. It's also called the fundamental frequency. All right, so that is the fundamental frequency. That's also how you pick frequency out of a frequency domain plot. But it can get a little bit more difficult. All right, so it can get a little bit more tricky. You could have something where you have these harmonics, and your label only says 1,000 hertz, 2,000 hertz, not 200 hertz. So then, just like before, you know that you want to find the fundamental, but you don't exactly know where that is. You do know where the second harmonic is. So there are two harmonic peaks in, oh, that's not going to be right. There are two harmonic peaks in 1,000 hertz. So what you do is you take 1,000 and you divide it by 2, and you end up with 500. So then you know that your fundamental frequency is at 500 hertz. Great. You also know the spacing is the same between all of them, so then you can assume that frequency 2 is 1,000, frequency 3 is you're going to add the 500 hertz to 1,000, so it's going to be 1,500 hertz, then 2,000, then 2,500, then 3,000, then 3,500. Okay, there's one more thing we want to do, and that's how do you find the period when you know frequency? It's pretty simple. I think my handwriting is getting better on this. So period from frequency, we know that the frequency equals, I'm going to give you 2,525 hertz. All right. If you're a super nerd, you can follow along with me, and we're going to do a proof. So we have frequency equals 1 over t. Well, one way that we can start to move this to solve for t is we can multiply both sides by t. If we multiply both sides by t, we end up with ft equals 1. Okay, cool. But now we want t by itself. One way that we can get t by itself is dividing both sides by f. We divide both sides by f, t is by itself, and then we have 1 over f. If you want to see that worked out, hang on. I know not everybody just switches these things around in their head. 25, 25. remember that. Okay, so frequency equals 1 over t. So what we want to do is we want to come in with a different colored pen, and we want to say multiplied by t. Like all this gets multiplied by t, and this also gets multiplied by t. So then what that gives us is tf equals, and then these t's are going to cancel each other out, because this is like essentially saying t over 1 multiplied by 1 over t. So the t is on top, the t is on the bottom. They're going to cancel each other out. So we have tf equals 1. Okay, so then let's come down here. We've got tf equals 1. And what do we want to do to both sides here? Well, we want to divide both sides by f. So we want to take that and multiply it by 1 over f. And we want to take this 1 and we want to multiply it by 1 over f. Well, again, if f is on the bottom here and f is on the top, if f is on the bottom here, f is on the top here, they're going to cancel. And then this is going to end up going on the bottom of this fraction here. And so you're left with t equals 1 over f. So it's exactly the opposite of our other formula. You just swap what's on the bottom. Okay, so let's get rid of everything. And I've deleted part of my Q. That's okay. We know what it says. All right. So the frequency equals 25 hertz. So T, oh no, this again. There we go. T equals 1 over 25. And if I look at my calculator, that is 1 divided by 25. 25 is 0.0003996. So let's just round it to 0.0004. If you want to check that, just do 1 divided by 0.0004 and you get 2500. It's close. And rounding is totally acceptable. All right, that's it.